Okay, so first I want to remind you that the first homework 1 has been uploaded. Is due next Friday. Okay. Till next Friday. Okay, so then let's continue the Lagrangian mechanics. Okay. So last time I introduced this principle of least action, right? So and then from there we get to the Lagrange equation of motion, or known as the Euler-Lagrange equation, right? So and that Lagrange equation of motions, right? So of course it will be a differential equation, and the differential equation that we obtain from this Lagrange equation of motion would be the same as what you get from the Newton's second law, right? And then what I also told you last time is that when we use different coordinate system, right? So Cartesian coordinate system or polar coordinate system, right? So the form of the Newton's equation, right? So would be different, right? When you use different coordinate system, right? So, however, the form of the Lagrange equations would be independent of the coordinate system that we use, right? So before we move on, so last time I introduced this polar coordinate system, right? So and then we need to describe the motion of particles in this polar coordinate system, and I told you that sometimes it would be more convenient to do that, right? So here let me reiterate, okay? So the concept of using polar coordinate system, okay? Before we move on to the next example, okay? So again, we'll consider a two-dimensional plane, okay? So and suppose I have a particle, okay? So a particle over here, and then the trajectory of the particle, okay? Suppose looks something like this, okay? So that is this red dot is moving like this over time, okay? So and if we are doing the Cartesian coordinate system, right? So first of all, let me also draw the velocity vector, okay, on the same picture. So you know that the velocity vector, okay, so must be tangential to the trajectory, right? So this is the v vector. Okay. So now, if we use the Cartesian coordinate system, right? So you understand that we can just decompose it into the x component and the y component, right? So then I have this this component here along the x direction, and then the other one that is along the y direction. And you know that this one, right? So then the magnitude of this one, of course, is x dot, right? And then the magnitude of the other one is y dot, right? So this is how we would do it in the Cartesian coordinate system, right? So this v is x dot x hat plus y dot y hat. Right? So now, if we use polar coordinate system, right? So what we do instead is that first, let me draw a line that joins the origin and the particle position. this time, right? So you remember that we have two unit vectors that we will think about, right? So this is the R hat and the theta hat, right? So you must still remember that the R hat is the vector that is go along this radial line, right? So this one. Okay. So therefore, now I'm decomposing this V vector, okay? So in a different way again, okay? So this time I'm decomposing this V vector into the what I call the VR and the V theta. So like this. So this is VR and this is V theta. So you can see how it is different from the Cartesian coordinate decomposition, right? So, and that is, right, this VR is just this component, right? So of this V vector along the radial direction. And then this V theta is the component of this V vector along the, what we call the transverse direction, okay? So, and last time we have derived already that this VR is R dot, right? So this distance is R, right? And then this V theta is R theta dot, right? So that is this R dot is describing how fast, right? So this particle is moving away from the origin. So this R dot here. And then on the other hand, right? So this V theta is that if you imagine that this instantaneously this particle is moving like along a circle, right? So then this R theta dot is basically the R omega that you have learned before, right? Okay, so that is right. So in polar coordinate system, right? So the V is given by R dot R hat plus R d theta dot theta hat. Right? And as I said last time, so remember one great difference between this system and this system is that x hat and y hat, the two unit vectors, right? So they always stay at the same direction, no matter where your particle is, right? So, but then in the polar coordinate system, right? So this R hat direction and this theta hat direction will actually depend on the position of your particle. And then last time, right? So from this VR and V theta, right? So we take the derivative, right? So I also show you that the acceleration, right? So now if I talk about the acceleration, then I can also decompose it into this radial direction and this theta direction, right? Okay, so that is right. So the acceleration vector, right? So can always be written as this AR R hat plus this A theta hat. Okay. So now if we talk about the equation of motion, right? So that is now that if I tell you that, okay, so there's this particle, right? So it's under the influence of some forces, right? Such that it moves like this, right? So then let me try to draw the force. I mean, I don't exactly know how the force would be, but suppose if I just draw the force like this, okay. right? So then if you want to describe the equation of motion, right? So using the polar coordinate system, right? So what you need to do is that you need to decompose the force, right? So also in the two directions like this. Right, so you need to decompose it into the radial direction that I call is FR, and then the other I call this F theta. So then the F equals MA, right? So would give me this FR R hat plus this F theta hat equals AR R hat plus A theta hat times M, of course. Okay. So then you have you end up with two equations, right? Is that FR equals MAR and F theta equals MA theta. So now let's move on to the example that I want to talk about. Okay, using this polar coordinate. Okay. So this is again an example that you know how to solve already. It's just again it's a projectile motion under constant gravity, okay, pointing downward. Okay. So first of all, right, so I want to remind you that in fact for this problem, so you have already used the Cartesian coordinate to solve it, and it was very easy. Okay, so and in fact polar coordinates won't be a convenient choice of this problem. Okay, so but at least I want to use this example to illustrate how we use the polar coordinate system. Okay, with the equation of motion. So this is the trajectory of the particle, right? So this, suppose at some time t the particle again is here. Then as I said, right, so before, right, so you if you want to use polar coordinate system, you always want to decompose everything in the radial direction and the transverse direction, right? So the force, we know that the force is points like this, okay, mg. Okay. So now I want to decompose it, right? So that is one component is like this, right? And then the other component is like this. Okay. So this is theta, right? So that means that this is also theta. So now if you just take this triangle, right? So you can see that this component over here is mg sine theta. And then this one is mg cosine theta. So in both of them, right, so this is the magnitude, but in both of them, we are going to add the minus sign, because this one, you know that it's pointing towards the direction where it's going to the decreasing the r, right? So because it's points like this, right? Also, because it's points like this, so this direction will tend to basically decreasing the theta value, right? So that's why I add this minus sign. Okay. So therefore, right, so I have this radial component of the force and the transverse component of the force, right? So then my equation of motion, right, so along the radial direction is this one, right? This is m. This is this whole thing is AR, right? So the acceleration in the radial component equals FR, right? The other one, well, m a theta equals this F theta, So this is how we would set up the equation of motion, right? This with this Newtonian way. Okay. So now let's do the Lagrangian method here. Is that now we don't think about force, but we think about just the kinetic energy and the potential energy. Right. So and remember that for the kinetic energy, right? So it's 1/2 mv squared, and because we are using polar coordinate system, right? So then we need to do this 1/2 m, the radial component of the velocity square plus the transverse component of the velocity square, like this. And I just told you that this VR is R dot, right? So that is this R dot square. And then I also told you that this V theta is R theta dot, so it's R theta dot square, right? So this is the kinetic energy. And then the potential energy, right? The potential energy is that you need to consider this height over here, right? So this height is y, right? And y we know that this is actually equals to r sine theta, right? So then instead of writing as mgy, okay, you should write it as this mg r sine theta. So then kinetic energy and potential energy are all ready, right? So this looks like this, right? So now I have this Lagrangian, right? So in terms of r and theta, then we just use the Lagrange equation. Okay. So as I said, right? So the form of the Lagrange equation is invariant, right? So under a coordinate transformation, right? So your x, y, or r theta, the form looks the same. Okay. But anyway, after you actually plug the Lagrangian to the Lagrange equation, right? So you get the two equations of motion, and you will be able to verify that these two, of course, again, will be the same as these two over here. Okay. So we will, of course, use polar coordinate system again. Okay, so maybe actually not too much in this chapter, but as I actually told you last time, is that if we consider the central force problem, right? So the Earth orbiting the sun, that kind of problem, we'll definitely use polar coordinate system. Okay, so I can tell you why first, because in that case, right? So when I say central force, that means that the force is always pointing from your particle to the origin. Okay, so in that case, then it is convenient to decompose the equations of motion in using polar coordinate system, right? Because in that case, you only need to have FR, okay, but not F theta. Okay. Okay, so the next example, again, this is a system that you are already familiar with. Okay, it's this simple pendulum. Okay, so this is a mass connected to a massless string, right? So and then it's pivoted over here, right? So it's just doing a motion like this, the pendulum motion. So and right, so I'm sure that you know how to do it in the Newtonian way, right? So but let's take care of it in using the Lagrange equation. So again, right? So the Lagrangian, right? So the kinetic energy and the potential energy over here. So one thing that is special here is that, okay, again, here we are using Cartesian coordinate system, right? Okay, no problem. And we have x and y, right? So two numbers. But you already know that actually it is in this case, right? So the particle is not really free to move anywhere, right? So on the entire plane, right? So it actually just move like this, right? So it's because of the fact that the length of this string is fixed, right? So and I assume that is always this string is tight always. Okay. So and therefore, right? So although we use this x, y two numbers to represent the coordinate, but there's actually one equation which I call the constraint here, right? So to tell you that it's always have to move along this circular arc, right? This x squared plus y squared is always equal to this L squared, right? So that is, right? So now you can see that although in the Lagrangian, I'm writing two variables out, right? But in fact, you know that it's really just one variable is sufficient because the x and y has to satisfy this constraint. Okay. So now, okay, so if I actually just eliminate, okay, if I actually just eliminate one of the variable, okay, so let's say I eliminate the y variable, okay, so you can do that, right? So you can actually just substitute. What you can do is that, right? So from here, you can write down this y equals L squared minus x squared, right? And then if you substitute it to the Lagrangian, right? So and of course y equals to this, and then that means this y dot equals minus x L squared minus x squared x dot. Okay. So if you substitute this one and this one to the Lagrangian, right? So you can show that the Lagrangian has this form, right? So everything just in terms of x, right? No y anymore. Okay. So because I only have one coordinate, right? So that means that one Lagrange equation is enough, right? So but if you actually go ahead and try to plug this L of x, right, into this Lagrange equation, you found that the equation of motion that you get is quite messy actually, right? So and this is just to illustrate that, right? So in this case, right, so this xy is not the convenient choice for your coordinates variable. Okay, and you actually know that what coordinates that you use, right? So is that when you first learn about the pendulum problem, I'm sure that you use, right? So this theta as your variable, right? So to study equation of motion, right? So here, if we do the same, right? So I'm going to set up the Lagrangian. It will looks like this. Okay. So this is just the R omega, right? This L theta dot. Okay. So in this case, right, so you go ahead and apply the Lagrange equation. A much simpler equation of motion can be obtained. And of course, this is something that you are familiar with, right? Theta double dot plus G divided by L sine theta equals 0, right? And then I'm sure that you also know that, okay, for theta to be small, then this sine theta is just approximately equal to theta, and then you solve out the sinusoidal solution, right? Okay, so now one more again. So in these few examples are all simple examples in the sense that I'm sure that you've seen all these problems, right? So in your first year course, right? So if this pendulum, this projectile motion, and then this inclined plane, but here, right? So we just use the Lagrangian to re-examine the problem. Okay, but later on, okay, we'll soon have more complicated examples. Okay. So this one, right? So as I said, what you've seen before, right? So this is just a particle sliding along this inclined plane, right? So this time, right? So let me again, right? So I can just use Cartesian coordinate system, right? So then this is the Lagrangian that we'll get. Okay, so and again, right? So it is not really free to move anywhere on the XY plane, right? It's just free to move along this line. So again, I can write down this so-called constraint equation, right? Is that the XY coordinate need to satisfy this relation. Okay. So that is, again, this is really not a Lagrangian of two variables. Really, just one variable is enough. Right? So if I just plug this equation over here, right? So just keep the y variable. So this is the Lagrangian that I will get. And then this is the equation of motion that I'll get. Okay. And I'm sure that when you first learn the problem, right? So this is not, the y is not the coordinate that you use, right? Instead, you use this one, this I call s as your coordinate, right? So this s is just the distance measured from the top edge of the inclined plane to your particle, right? So, and because in this way, right? So when you do the Newtonian mechanics, right? So what you do is just that you have this mg right over here, and then you just decompose it into this mg sine theta and this mg cosine theta, right? And then you immediately conclude that this s double dot is g sine theta, right? So this is how you did it, I'm sure. Okay, so but here again, so go through it quickly. That now I have this Lagrangian in terms of s, right? So not in terms of y. Then my kinetic energy is just m s dot squared. Okay. And then this potential energy now is written as mgs sine theta. Okay. So be careful about this plus sign over here, right? So here this minus sign is because now we define the distance from here to here, right? So from the top to the lower, right? So before that, I define the distance from below to up, right? So that's why when you write your potential energy will be off by a minus sign. But anyway, right? So now that you have write down this Lagrange equation, right? So here you can see that I don't need to worry about the constraint anymore, because now the fact that you write this one as your variable is that you have already take the constraint into account, right? So it's that you know that the particle is going to slide like this along this plane. Okay. So you start off with just one variable. Okay, instead of here, you start with two variables and then write down the one constraint. Okay. So and then a Lagrange equation, and you get this, same as what I just told you. Okay, so from the previous example, okay, you can see that we really have different ways to use the coordinates, right? So we don't need to always use the Cartesian coordinates, right? Especially now that we know the form of the Lagrange equation, right? So it's invariant, right? So under different coordinate transformation, right? So then we are free to really select the kind of coordinates that we think are more convenient, right? So for example here, right? So instead of using this x or y, right? So obviously theta is more convenient. So then now I'm going to introduce a concept that is a so-called generalized coordinate. Okay, so it's just a fancy name, but I believe this is something that you have somehow used before, okay, without really knowing this term, right? So what I'm trying to say is that again, right? So if I'm going to consider a 2D plane, right, xy, and my particle is over here, right? So if you just use the Cartesian coordinate, right? So then you use this xy to be your coordinates variable, right? So, but just now you see that from these two examples. So I'm using this data, and then here I'm using this S, right? So these are also variables that can describe the motion of your particle, right? So then we call any of the set of the variables that can describe the motion of your particle as the so-called generalized coordinate. Okay. So let me give you one more example, a few more examples here, right? So for example, if I am going to consider a system which consists of a dumbbell, right? Essentially, so like two particles, right, joined by a massive rod, right? So how would you describe the motion, right? So of this system, okay? So what coordinates would you use? Right? So again, right? So you can still use the Cartesian coordinate for the two particles individually, right? So this x1, y1 I call, and then this I call x2, y2, right? So if you tell me the x1, y1 values and x2, y2 value, then I can completely describe, right? So the motion or the state, right, of this system of two particles, right? And in fact, right, so you do not need all four numbers over here, right? So because you know there's one constraint, right? So the constraint is that, let's say, right, because this length is fixed, because this rod I assume is rigid. So the constraint is that this L has to be, right? So it's related like this, right? So it's this x1 minus x2 square plus y1 minus y2 square. Okay. So that is, right? So in this case, you actually just need to give me three numbers. That is sufficient to describe the entire system, right? Because if, let's say, if you have x1, y1, and x2, you give me these three numbers, I will be able to obtain this y2 from this constraint. Right? So this case, right? So three, we say that, okay, so then this, then I can say that, right? So this x1, x2, and this y1 can be a set of coordinates or a set of generalized coordinates that for us to completely describe this system. So, however, right? So there's a more convenient way to do it, right? Is that instead of having these four numbers, what I'm going to do is that I'm just going to tell you the coordinates of the center of mass of this system, okay, which I call xm and ym, okay. And then, so I give you two numbers, and then I also give you the angle between this rod and the x-axis. Again, I can call this theta. Right. So this theta is not really the theta in the polar coordinate, but I call this theta anyway. So that is, this is a first choice, right? The first set of generalized coordinates that I can describe the system, right? So then the second is that I can use xm, ym, and theta, these three variables, to also describe the system. Okay. And in fact, right, you might imagine that the second set of choices is actually more convenient than this one. Okay. So, right, so this is a set of generalized coordinates, right? So this is the other set of generalized coordinates of the system. Okay. So, and here, right, so you can kind of also have a feeling that, so how many generalized coordinates we need to describe the system, right? Here you can see that if I have two particles, so if I have one particles, two numbers, right? Two particles, four numbers. But at the end, I just need three because four, but minus one constraint. So 4 minus 1, you just need 3. Right? And if you go back to, for example, this example, this pendulum again, right? So if you have one particle, in principle, you need 2, right? If it's just on the XY plane, right? So, but then you have one constraint over here, right? So then actually you just need 1, right? And that 1 can be here X, right? Or this theta. Okay, so if we just, well, just a simple generalization, right? So if I now talk about three-dimension motion, right? So the particle is no longer just confined along the XY plane, right? So if I have this one particle, right? So here, and then of course I can just say X, Y, Z as the three coordinates, right? And of course, you know that in this case you can use spherical, right? So R theta phi or cylindrical R phi Z. Okay. But again, now if we just consider some special problems that we have some constraint, right? So suppose I have a pendulum. So let's say this is the ceiling, and then the end of the string is fixed over here, right? So and then I have a particle over here. So this time, right? So the pendulum is no longer can just do this plane oscillation motion. It can also goes like this. Okay. So just like a circle. So that is, it can go like this, or it can go like this. Okay. So then in this case, right? So what coordinates you think would be convenient to describe this problem, right? So again, right? So you can do X, Y, Z, right? So you can still use this X, Y, Z, but again, this time I have a constraint. So this string, this length is L, right? So you can just after you write down X, Y, Z, you also have to tell me that that is a constraint like this. So I assume that this point is the origin. So and so this is one set of the choices, right? So you can just have X, Y, right? Z can be obtained from this equation. But again, you can imagine that this would not be the most convenient choice for you to describe this pendulum, right? So instead, why don't we just use two angles? So one is again this theta, right? So this theta is the angle between a vertical line and this string. Right? And then the other one, I guess you know the answer is the phi. It's phi over here. Again, the azimuthal angle. Then in this spherical, this pendulum, right? So you can, again, you can use two coordinates, theta phi. So to be a set of generalized coordinates. Right? So why 2, right? So because, repeat again, now I have one particle in 3 dimensions. That means I should have 3, but then I have one constraint here. So that's why I only need 2. So one more example. Okay, so suppose now I have, again, I have this particle over here. So let me just use this figure. But it's confined to move along the surface, inner surface of a cone. So this is a cone. Okay. An inverted cone. Okay. So and then my particle is sliding along the inner surface of the cone. So then this time, right? So again, so what do you think is the convenient way to describe the motion of this particle? So you can use two numbers. So first is that you can first use the distance between the origin and your particle. So this green line here, that's my first variable. Okay. And then the second variable that I'll use is this one, right? So this angle over here. Again, it's just a phi angle, right? So that's movable angle. Right? So in this case, right? So I can just let me just write down here. So this is S, this is phi, right? So the S and phi can be a set of coordinates, generalized coordinates, right? So here, as I told you before, theta and phi. So that's the idea of the so-called generalized coordinates, right? Is that you use whatever variables. It can be in the unit of length. It can be in the unit of angle. It can be an angle, right? So angle does not have a unit, but and just whatever, and it can be a combination of both, right? So as long as that set of variables, that set of coordinates are sufficient to completely describe your systems, then that would be a set of generalized coordinates. So these are just repeating what I just said. Okay, and you can see that the set of generalized coordinates won't be unique, right? You have different ways to describe the same system. Okay. So that in general, right? So I would just call a set of generalized coordinates as this Q, right? So from Q1 to Qn. Okay. And then well, as long as, right, so they are all independent. So I assume that they're all independent. Now you have already used the minimum required number, suppose, right? So taken all the constraints into account, right? So then after that, you can just use the same form of the Lagrange equation, right? So that's the nice thing, right? So you don't need to worry about the coordinate that you use, because the form of the Lagrange equation always invariant. Okay. So, and these are again just repeating what I said, right? So you can just try to read it again when you do revision. Okay. So next, okay. So let's take a 15 minutes break here, and after that, more difficult examples will come. Okay. Okay, so let's continue. Okay, so now we'll have more difficult examples. And so this one, I would just put it as an optional one. Okay, so is that you won't see a problem similar to this in your homework or test. Okay, so but I want to talk about this because again, this is a very classic problem. Okay, so and this problem again is related to the cyclone. Okay, so remember the brachistochrone problem, we say that the solution, right, so is a cyclone. Okay, so now this problem is actually known as the catachrome problem. So what we are considering over here is that suppose I've already set up a cyclone, path like this. Okay, so a full cyclot path. Okay, and then basically you just put a particle, okay, somewhere, and then just release it from rest. Again, the whole thing is under constant gravity, right? So you could imagine that what this particle will do, right? So it just slide to the bottom and then up again, and then slide back and forth like this. Okay. So, and then you could imagine that it's somehow like a pendulum problem, right? So, however, if it is really a pendulum problem, right? So this one should be a circular arc, right? So which I draw this dashed line over here, right? So if it is a circular arc, okay, so it will look more like this, okay. So, and the cyclot, you can see that the curvature, right? So at different parts will be different. You can see the deviation between this red line and this dash curve over here, right? So for a circular arc, so everywhere the curvature would be the same, right? But for the cyclot, that's not the case. Right? So so the cartogram problems, so basically what it means is that we want to construct a curve, which I already told you the solution is a cyclot, okay, is that if I just let it slide, right, so then you can calculate the period of this one complete cycle, right, or one oscillation. You can calculate the period. And if you just change the amplitude of this motion, that is, instead of releasing from rest at this point, right, so you release from rest over here, right? So again, so then the oscillation, of course, will be bigger, will be a larger amplitude. And you can, again, like calculate the time taken to finish one oscillation, right? So, and if it is an arbitrary curve, right, so it's very likely that you will obtain two different numbers, right? So, and it turns out that, okay, if you are doing this motion, right, along a cyclot, right, so the period of one oscillation is independent of the amplitude, right? It doesn't matter whether we release it here or here or here, right? So the time taken, right, so to finish one oscillation is a constant. So that is what we call it a cartogram problem. Okay. So if I again remind you about the simple pendulum, right? So if I remind you again the simple pendulum problem, right? So you may still remember that, right? So again, if you do the small angle approximation, right? So this theta dot is roughly equals to minus g divided by L theta. And then you will conclude that, right? So the period is 2 pi L divided by G, right? This is something you have learned before, right? So for this simple harmonic motion, right? So the period, right, is also, right, so independent of the amplitude. Right? However, you have to remember that this equation is just approximate, right? Is that you have already made the small angle approximation to get to this, and then to get to this, right? So that means within the small angle range, the period is independent of the angular amplitude, right? However, if the amplitude here is quite large, that is the angle, the theta value is large, right? So then you have to exactly use this equation instead of this equation. Okay. So then this one is no longer a linear or a simple harmonic motion, and you will find that if you exactly solve this, right, so you'll find that the period actually will be depend on your theta amplitude. So but here, right, so what we are looking for is really without any small displacement or small angle approximation. Okay, so the period will be truly independent of the amplitude, right? So no matter how large it is. Okay. So you could, again, I have this circular arc here, right? So you could imagine that if you have a pendulum, I talked about 2 seconds ago, right? So then the particle will slide like this. Right? Okay, so let's see how to formulate the problem. Okay, right. So Lagrangian. Okay, so I am going to. This is again just a 2-dimensional problem, right? So if I use take the kinetic energy and potential energy, right? So this is what I have, right? So but again, right? So this is a problem with a constraint, right? So because this particle is just sliding along this curve here, right? So that is x and y has to satisfy this relation over here. This is the equation of the cyclone. So in principle, right? So what you can do in principle, right? So you can eliminate x or y, right? So by using this, right? So you can express, for example, express this x dot square, right? In terms of this y and y dot, right? So then you make the whole thing just contain one coordinate variable y, right? So then you use one Lagrange equation, then you can solve out the y as a function of time, right? So in principle. However, if you actually try this, you realize that it will contain a very complicated expression, right? So in terms of this y and y dot, right? All because of this sine and cosine over here. Okay. So here, right? So let's pick a more convenient generalized coordinate. Okay. The generalized coordinate we pick this time is this length. Okay, by itself is a curve already. Okay, right. So the arc length of the cyclone measure from the bottom of the particle position. Okay, so this is the generalized coordinate that I need to use. I want to use. Okay. So that is I need to convert this Lagrangian over here, right? So to be in terms of S and S dot. Okay, so I want to do that. So let's see how it's done. Okay. So this part, the kinetic energy part is easy, right? So because we know that, right? So just from the picture, we know that the velocity will be the rate of change of this S, right? So the velocity is just S dot, right? So that's why kinetic energy is just this S dot square right here. However, we need to express the y in terms of S, right? Because of this Lagrangian of this y, right? So I want everything in terms of S. Okay. And here I need a plus here. Okay, so then to express S in terms of y, right? So I need to calculate this arc length. Okay, so this is S, right? So and this is the integral of the square root of this dx squared plus this dy squared. Okay. So and of course, what you can do is what we did before, right? So what we did before is that you convert this one to something like this. Right, so this is what we used before, right? So, but in this problem, okay, it's much more convenient to use the other variable. Okay, that is, I'm going to use the theta as my integration variable. Okay, why is it convenient? Because my x and y is already expressed in terms of this parametric form theta. Right, so that's why it's convenient to express this whole integral as a integral of theta. Okay, and I have this lower limit and upper limit that I will explain. Okay, so but first of all, right, so from this picture, you can see what theta means. right? So remember how a sine plot is formed, right? Is that you put a wheel on the floor and then you let it roll, right? So you just imagine that originally you have a wheel that is over here, right? So and at this and at the beginning, okay, so this is theta equals 0, and then you just let it roll like this, right? Always touching this plane, right? Roll without slipping, right? So and then this is the point that you put a marker, right? So as it roll, right? So this point will trace out a trajectory like this, right? So and as it roll, the theta value will increase, right? So as a function of the distance that it rolled. And then as this one finally go here, right? Then it completes one complete revolution. That is 2 pi, right? So and when this wheel is exactly at the middle, right? So you could easily know that over here the theta is pi over 2, right? So because I'm talking about this arc length over here, right? So and I has to start my wheel at this point, which is theta equals pi over 2, right? And then let it roll. So and now when it's up to this point, okay, the question is what is the theta value? Okay, and I tell you that the theta value is given by this one. Okay. So why is it? Okay, so let me explain it first and I'll continue. So look at this wheel over here, right? So this is the one that is drawn over here. Okay. So let me try to draw the S also in this picture. The S is something like this, right? Sorry. The S is something like this, right? Right, so this is the S. So what I'm doing here is that I want to try to relate this theta, okay, with this y value over here. So this y value, that means it's the y coordinate of this particle. Okay. So first of all, right, so we understand that when we are over here, y is always a negative number, right? So that's why the distance between the top edge of the wheel and this point is given by minus y. Okay, the distance. Because y is already a negative number, if I just want to find the magnitude, I need to have this to be minus y. So this is minus y. Okay. So this minus y would be equals to this part, right, plus this part over here. So this part, A, is just the radius of your wheel. Okay, I put it here. And then I introduce another angle, which is the beta. And then, so that's why this part over here is A sine beta. Okay. So, and now I want to express this beta in terms of theta. That's easy because 90 degrees or pi over 2 plus theta plus beta is equals to 2 pi. Right, so that's why beta would be equals to 2 pi minus theta minus pi over 2. Okay. And this sign of this thing minus pi over 2 right, can be written as minus a cosine 2 pi minus theta. Okay. And that is theta would be equals to this. Okay. So therefore, right, so I'm able to write down my upper limit as this, right? This upper limit is a number that depends on y. So this is what we want. Why do we want this? Because in the beginning, I told you that I want to express y in terms of s, right? So because then here I'm trying to find the relation between s and y, right? So then you can imagine that after I actually carry out this integral, I will have an expression that is a function of y. So that is s equals something y, right? Then I can go back to find y in terms of s. Okay, so this is the upper limit. Okay, so and I will skip one case is that in fact there are two cases that I strictly speaking that I need to consider, right? So case one is that this particle is right over here, and then case two is that this particle is up here, right? So in this case, right, so this beta would be positive, right? So and then in the second case, this beta is actually go up. This beta is negative, but just from the same very similar idea, you can see that I also obtain the same expression. Okay, so let's actually deal with this dxd theta and this dyd theta. That would be straightforward because x as a function of theta, y as a function of theta, right? Just take the derivative and plug it back over here. So then this is what I have. Okay, so and you can see that some simplification can be done because I have this cosine square theta and sine square theta, right? Just expand it and then do the simplification. You find that this whole thing is just 2a sine theta divided by 2. Okay. So luckily, right, so this one is not difficult to integrate, right? So if you integrate and then substitute the lower and the upper limit, then this is the expression that you get. Okay. So now you successfully obtain this relation between s and y, right? So, but we'll still need to do more manipulation, right? So just let me write over here. Okay, so this, if I take the square of both sides, okay, so I will have this s divided by 4a squared equals this whole thing. Okay. And next, I basically at the end I want to express y in terms of s, like instead of s in terms of y. Right, so here, this using this double angle half angle formula. Okay, so we express this one as this one. Okay, so now it's nice because I have this cosine and cosine. I can cancel this. Okay, so then it's quite simple actually. S divided by 4a squared actually equals to 1/2 2 plus y divided by 8. Okay. So then this is the difficult part, right? So this just carrying out this integral. But after that, right, so we will be able to express y in terms of s, and that's exactly what we want. Okay, so then I can write my Lagrangian in terms of just s and s dot, right? So that's very nice. So now this one over here, I will be able to look at it like this one, right? So you can see that what I'm doing here is just that I'm just writing out these two terms separately. Okay, so and now just look at the first two terms over here. Okay, so the last term is just a constant, right? So but the first two terms will depend on s dot and s. Okay, so see this and compare with an harmonic oscillator. If you have a harmonic oscillator, last time I think I mentioned that, right? So you just have a harmonic oscillator in one dimension, then this would be your Lagrangian. Okay. And now compare this form and this form. So this whole thing, as you can call this K, isn't the exact same form, right, as this harmonic oscillator. So the significance here is that we did not make any small angle approximation, did not make any small displacement approximation, right? So, but this Lagrangian looks exactly like the Lagrangian of a simple harmonic oscillator. Then at this point, right, so you can just go ahead and use the Lagrange equation, right? And then this is what you get. Okay. This is, of course, is for S, not for Y. So then from this, right, so you know that the omega, right, so the omega of the system is this square root G divided by 4A. So that is your period would be 2 pi divided by omega, right? So 2 pi divided by, so 2 pi times 4A divided by T. So, and now, right, so you can see that, so this answers the question, right? So basically, right, so because of this equation, right, so you can conclude that no matter what kind of amplitude that you have, right, so the period of oscillation is always this. Okay. All right, I think I made, okay, sorry, this is minus. Yeah, minus. Okay, so now, okay, so next example. Okay, so this is also, I believe, is something new, okay, to you. You have definitely, well, seen this fixed inclined plane problem or fixed wedge a lot of times, but this time we are going to allow this wedge to be movable. Okay, so what happened is that you could imagine that because as it slide down, right, so there's always an action and reaction pair happening over here, right? So this and this. So therefore, so this is the floor, I suppose, right? So now I consider this one to be frictionless. So then as this particle slide down, right? So then of course this wedge will slide to the right. Okay, so because of this reaction force over here has the component, horizontal component to the right. Right. So therefore, right, so if you consider what happened next, right, so it will looks like this. Right. So let me right, so let me show you again. So the fixed wedge, right? So after some time, it just goes like here. Right. So if it's a movable wedge, right? So after some time, it goes like this. Right. So this fixed wedge move a little bit to the right. Right. So this particle actually slide down, but it's also follow, right? So it's always touching the wedge, right? So actually go down a steeper slope, right? So compared to this one. Okay. So now I want to try to solve this problem. Okay, over here, and I'm going to show you both using the Newtonian equations and also the Lagrange equation. And this might be an example where you can appreciate that, yeah, sometimes maybe using Lagrangian and Lagrange equation is easier, okay, to solve the problem. Okay. So originally I wanted to talk about the Lagrangian first, but actually I will do the other way around. Okay. So is that I'm going to use the Newton's equation first. Okay. So and then I will come back to the Lagrangian. Okay, so this is the system, right? So this time, right? So the two coordinates that I'll use, the two generalized coordinates that I'll use are the following. Okay, is the x and the s. Okay, what are the x and s? Right, so written here, right? So the x is the distance between this edge of the wedge and its initial position, right? So you just imagine that initially, right? So the wedge is over here, right? So because it's keep moving to the right, right? So then there will be a distance x, right? So that's the x. So and then the other coordinate that I will use is again this s. Okay, is that it's measuring the distance between this particle position and the top of the wedge, this s. Okay. But there's one thing to be careful, right? Because now, right, so you need to imagine that this s is a distance that measured by someone that is moving with the wedge, right? So you just imagine that you are actually standing on the same wedge, and then you take this s. Okay. So because this point itself, this reference point itself, is also always moving. Okay. So this is the s. Okay, with a moving reference point. So then let's set up the equation of motion, right? So I know, right? So this is of course more difficult than the case with the fixed wedge, but however, right? So all we need to do, right? So again, is to look at the forces. Right? So I already told you the pair of action and reaction, right? So I just draw it again over here. And then the other one, of course, is the gravitational force. Okay. So, of course, the gravitational force also acting on the wedge, but that's irrelevant, right? So because the wedge is not going to move up or down. So now let's set up the equation of motion. Okay, so let's first look at the wedge. So, and the only motion that we need to care about is along the horizontal direction, right? So what is the force acting on this wedge horizontally, right? Would be this component over here, right? This would be r sine theta, right? So then the F equals ma is r sine theta equals the big M times x double dot, right? So this is for the wedge. So then the other one, of course, is for the particle. So for the particle, so we are just going to again, right? So look at the two directions, not horizontal and vertical, but instead I'm looking at the one that is parallel to the surface of the wedge and then perpendicular to the surface of the wedge. Okay. So first, right? So let's look at the parallel. So here, the thing to be, well, first you can still quite easily find out the force, right? So because still, right? So the r is perpendicular to the surface, so that won't be irrelevant to this equation. And the only component again acting parallel to the wedge surface would be due to the mg, right? So this would be the mg sine theta, right? So therefore, the force that we talk about here is mg sine theta, okay? And it's equals to what? Equals to the acceleration of the particle along this direction. So if the wedge itself is not moving, then of course the acceleration, the m times a, is just this one, right? However, now the whole thing is moving right to the right, right? So that is, you just consider this whole thing as one system that is having this acceleration to the right, right? So including this particle, right? So this particle is part of this system, okay? So therefore, right? So if I want to consider, right? So the acceleration of the particle along this direction, I also need to take this one into account, okay? So let me write it again. So this one, x double dot, by pointing to the right, I can also break it down into two directions, right? So one is this, and the other is this. So I intentionally break it down into these two components, right? Again, this one is just parallel to this surface, and then this one is perpendicular. So that is, this is x double dot cosine theta, and the other one is x double dot sine theta. So therefore, the total acceleration, the net acceleration of this particle is actually s double dot minus this one, x double dot cosine theta. Okay. So that's the equation of motion along this direction. Okay. So now, along the other direction, the perpendicular. Perpendicular. Now, this time, what forces do we have? We have this mg cosine theta this time, right? So this is mg cosine theta, and also the reaction force in the opposite direction. So mg cosine theta minus r, and this will be equal to m times some acceleration again. Again, if this whole system, this wedge is not moving, right? So there won't be any acceleration of the particle along this direction. But again, as I said, right? So because the whole thing is moving, right? So then this x double dot acceleration will give this component, right? So this x double dot sine theta. Okay. So that's what we have. Okay, you can see how is it, of course, more complicated than the fixed wedge. Okay. Okay, so now at the end of the day, so what I want to solve for the motion, right? So that is, I want to find x as a function of time and s as a function of time. And I now have three equations. I also have three unknowns, right? So s double dot, x double dot, and the r. And r is the one that I don't care, right? So I just basically need to substitute this to this term over here, right? So and then solve these two equations. Then I have two linear equations, two unknown, right? So x double dot and s double dot, and of course I can solve for s double dot and x double dot, and then just integrate them. You will get s and x as a function of time. So this is how we would deal with the problem, right? So using the Newtonian way. So now let's go to the Lagrangian. Okay, so for Lagrangian, right? So we don't need to care about the forces, right? So we need to care about the kinetic energies, right? So we have to be able to write down the 1/2 mv squared, right? So for the 1/2 mv squared, of course, I would have to have two terms. So the 1/2 m, the capital M, right? So the V, right? So this is for the wedge, the kinetic energy for the wedge, and then of course the other is the kinetic energy for the small m, the particle, right? This is what we are trying to do. So the velocity of the wedge, of course, is simple. It's just this x dot. Okay. So and now, right? So the thing to be careful is the small vm, right? So the velocity, if you look at this, right? So it will be pointing like this, right? So the horizontal component of the particle velocity, right? So would be this x dot minus s dot cosine theta, right? So because, so let me just draw the s dot first. Okay, so this is my s dot, right? So and then this component over here, horizontal one, is this s dot cosine theta, right? And then this vertical is my s dot sine theta. So therefore, right, so the total horizontal component of the particle velocity would be this s dot component, s dot cosine theta plus this x dot, right? But they are opposite to each other, so that's why I have this x dot minus s dot cosine theta. So it doesn't matter whether I do the other way around, right? So whether it's positive or negative, because we are going to take the square anyway. Okay. So the next one, right? So the vertical component of the particle velocity, right? Just this s dot sine theta. Right. So then we have the kinetic energy, right? And the potential energy was still simple enough, right? So because I just need to consider how far it has fallen from the top edge. Okay. So that's why my Lagrangian looks like this. Okay, the first this green term, right, is this term, right? So the kinetic energy for the wedge, these two terms are the kinetic energies of the particle. Final term is the potential energy of the particle. Right. You can see that in terms of x dot, s dot. Right. So this is the Lagrangian. So next, of course, is to Lagrangian over here, and then the Lagrange equation. Right. So the nice thing is that after you write down the Lagrangian, you don't need to worry about it, the vectors, the force. Now Lagrange equation, then you'll be able to get this two equation over here, and try to verify that you can see it right away. Is that these two are actually the same as the two that we obtained from the Newtonian method. Okay, and these two equations, two unknown. Okay, so you can also try by yourself. Okay, so to verify that this x double dot is given by this, s double dot given by this. Right. So first you can see that they have the right limit, right? So take the limit when n tends to infinity. Okay, if you do that, right? So then you can see that in this case, right? So the denominator will just becomes infinity. Then this x double dot is just 0. What you expect, right? And then in this case, right, I have this term goes to 0, and then this s double dot is just g sine theta. Right, so that's the limiting case, right? So that gives you the the fixed wedge case. Okay. So one more practice. Just now I take this x and s to be the set of the generalized coordinate. But I told you before, right? So that's not the only choice, right? So that I can always make another set of generalized coordinates, right? So this time I use this x1 and x2 to be my generalized coordinates. And at the end, you can compare whether this is more convenient or the previous one is more convenient, or they are just slightly not too different. Okay, so but this time you can see how I define the two generalized coordinates. Okay, so in the beginning, okay, so let's say the particle and the wedge both are along this line. So that is initially, right? So initially, the wedge is over here. Okay, so along this line, and then initially, right? So the particle is right over here. Okay, so I set this line as my reference. Okay, so and to define my x1 and x2. Okay, so that if I do it that way, right? So you'll be able to also write down the velocities of the two items, right? So velocity of the wedge is just this x1 dot, right? And this velocity of the particles written like this time. Okay, so and you can see that if I use this, right, so it will be easier to deal with the horizontal component. But then now the price to pay is that you get a more complicated way to write down the vertical component. Okay. But regardless, now I have this Lagrangian to be written in terms of x1, x2, x1 dot, and x2 dot. Right. And this, right, again, equation of motion can be found, right? So using the Lagrange equation. Okay, so there are 2 or 3 difficult examples I would say for today. Okay, so you might really want to go back and make sure that you understand how they work. Okay, so I have maybe 2-3 minutes left. I'll just spend these 2-3 minutes to introduce some terms. Okay, they are just names at this point for you to remember. Okay, so here, right? So again, I am just writing down the Newton's equations and the Lagrange equation. Okay, so on the left hand side, right? So you have the rate of change of momentum equals force, right? So if you break it down into the x, y, z component, then that's what you have over here. But on the other hand, right? So you have this Lagrange equation. I can break it down into this x, y, z, and then you have this 3 variables, these 3 equations over here. Right. So you can see that. Well, so one thing you can see, right? So is that this partial L partial coordinate dot will give you the momentum, right? And this partial L partial coordinates will give you the force, right? So therefore, right? So if you just compare the left and the right, so you will see that, right? So this, as I said, these derivatives give you momentum. These derivatives give you forces. Okay. And now, well, nothing's new, right? So let's just compare term by term. Okay, so momentum and force, right? So the definition of momentum and definition of force are still the same, right? So nothing new here. But now if I consider, right, so using the generalized coordinates, so not just x, y, z, right? So but any generalized coordinate that we have used, right? This time you don't have this partial L, partial x dot, or partial L, partial y dot, and so on. Now we have this, you have this partial L, partial Q dot, right? So, and of course this one, right? So may not give you the linear momentum, right? So you could imagine that if this is you're using the theta coordinate, right? So then of course you are not going to get the mx dot, my dot, and so on, right? So you're going to get the theta dot, right? So whenever, no matter what kind of generalized coordinate you use, whenever you take this derivative, we call this the generalized momentum. Okay. And if so happen that you have this xyz to be your generalized coordinate, then of course this one is just your linear momentum. And then this partial L partial Q, right? So it will be called the generalized force. Okay. And this generalized momentum, okay, is also called the canonical momentum or conjugate momentum. Okay. So again, let me use this simple example to illustrate that. Right. So this is, if I have this wedge example, if you take the partial L partial F dot, it gives you an ms dot. And you know that this is actually the linear momentum, right? So along this direction. And if you take the partial L partial S, you get your mg sine theta. And that would be the force along this direction. Okay. So what about this one? Okay, so this one, I'm not using xyz, right? So if I use this theta, if you take the partial L partial theta dot, okay, you realize that this one is not your linear momentum, but in fact, this is the angular momentum. Okay. And then this partial L partial theta, you realize that this is not the force, but is this the torque. Okay. But this case or the previous case, in both cases, well, we can call them is the generalized momentum and the generalized force. Okay, so next time I'll have a few more examples using the Lagrangian. Okay, and then we'll move on to the next part of the chapter.